Right, well, here we are. I was asked to tackle a Quora question about a cyclotron. So here goes. The question was, why does the increase in radius of a particle's path in a cyclotron decrease as the radius gets larger? It's a really nice diagram. I'm really thankful I don't have to draw that because my drawing is absolutely terrible. Someone wanted a little bit of extra clarification as to what this question actually means. What it means is that as the particle's going around in a circle in the cyclotron, why is it that if it's constantly getting more energy added to it, why does the next one get bigger by a certain amount, the next circle get bigger by a smaller amount, and the following circle get bigger by even smaller of an amount? The answer, in short, is kinetic energy, but I'll take a little bit of time to show you exactly what that means. So we'll pop over to here and take a look at our cyclotron radius problem. So we'll first start with our definition of kinetic energy, which is 1/2 mv squared. Just keep that in mind throughout the course of all that we're doing because we will get back to this toward the end. Next we have to think, okay, we're dealing with a particle that's going around in a circle. And so that means that it needs some sort of centripetal force in order to go around in that circle, in order to not just keep on flying off straight in another direction. So, given what we know from physics, the centripetal force is equal to mv squared over r. So now we know that if we had some sort of invisible string on the particle, keeping it going in whatever orbit it's going, it would need to have a force in proportion to the mass, the velocity squared, and inversely proportional to the radius. But since we don't have any imaginary string, we need to know what it is that's actually keeping the particle going. And what's actually keeping the particle going is a magnetic field. Was keeping the particle going in a circle is an actual magnetic field. That is equal to Q V B, where Q is the charge of the particle, V is how fast it's going through the magnetic field, and B is the strength of the magnetic field. So then what we wind up doing is we just set these two forces equal to each other. So if we go and say Fc is equal to the force of the magnetic field, we get mv squared over r is equal to qvb. We'll cancel out the v's and get mv over r is equal to q times b. So far we don't have anything necessarily useful yet, but if we go back to our understanding of kinetic energy from the very beginning, what we ultimately need to do is solve for kinetic energy. So what do we do to make this look like kinetic energy? Well, what we can do is we can take both sides, we can multiply it by v, or we could, there are lots of different ways of doing this. One of the best ways I can think of is square both sides. Yeah, you're going to square both sides of the equation, so you're going to get m squared v squared over r squared is equal to q squared b squared. And now to make it look more like kinetic energy, you just keep on messing with it until you wind up having 1/2 mv squared on one side of the equation. So you can get mv squared is equal to q squared b squared over m. And then we can just move the r squared on that side too. And then we can divide both sides by 2 and get 1/2 mv squared is equal to q squared b squared r squared over 2m. So now we can look, because both of these are expressions of kinetic energy. How does the actual cyclotron get kinetic energy? How does it increase the energy of the particle? I'll write down the equations here for reference. We get kinetic energy is equal to 1/2 mv squared is equal to q squared b squared r squared over 2m. So a cyclotron goes, and it is working at a constant voltage. Now voltage is exactly proportional to the energy that you can get from a charged particle. So because you're not having any weird variable voltage situations, but a cyclotron operates on an alternating current that basically when the particle goes one way through the gap, the current's going one way and it's accelerating the particle, and then when it keeps on going through the circle, it goes through the gap the other way. The current has alternated at this point. Current's pushing going the opposite direction. The voltage, the potential is completely flipped, and you force the particle to go even faster, and then you get through the gap again, force the particle to go faster, and it just keeps on going every single time you hit the gap. Now the energy, as the gap is a constant with the voltage is constant, the energy that you get every single time you go around one time around the cyclotron is the same. So if we go and think about looking at radius and think about velocity, if we're having constant increases in kinetic energy, so let's say we double the kinetic energy. Just to give you an example, if we double the kinetic energy, then what we wind up ultimately doing is if we double the velocity, that doesn't work. If we double the radius, that doesn't work, because if we double the radius, we're going to wind up getting 2 times 2 is 4 times the kinetic energy, and double the velocity, it's 2 times 2 is 4 times the kinetic energy. So it actually goes up by the square root of 2, or a factor related to the square root of 2. So that means it basically goes to show us that every single time that we put in a certain amount of kinetic energy with respect to our voltage, we put it into the cyclotron, and then what we ultimately wind up seeing is the velocity and the radius going up by a factor of square root of 2 over 2, or which is the same as the square root of 2. For every 1 unit of energy that you put in is going to affect the velocity and the radius by less than that. And so as the energy keeps on getting greater and greater and greater, as you keep on getting toward the edge of the cyclotron, the energy difference in between a particle traveling on a path of this radius and the energy to the energy of a path on this radius, the exact same distance, the difference in energy of that distance is exactly the same as the difference in energy in between those two is exactly the same as the distance in energy in between those two, etc., until pretty much you wind up getting the thing going so fast that you're getting really, really, really diminishing returns on velocity by putting just that little bit of extra energy in. And ultimately, when you get to that point, you're going to get close to relativistic velocities anyway, where all the rules go out the window and you can't use basic regular Newtonian physics and so on to explain the situation at all. So ultimately, to recap and to answer the question, it's because the energy differences from one orbit here compared to the orbit there is the same as the energy difference in between this orbit here and that orbit there, is the same as the energy difference in between this orbit here and that orbit there. If this is still unclear, hit me up. I know that I just kind of ramble on a little bit, and I'm putting this together in one take, and I have to get back to my translating work. So, hope this helps. See ya.